Hello everyone, my name is Vitali Prakapenka. I am Beamline scientist at GSECARS, running Diamond Annual Cell Program at Sector 13 APS. I would like to thank workshop organizer Hauja and Lisa for inviting me to give an overview of very exciting DAC program at GSECARS University of Chicago. As you may know, APS is finishing a complex upgrade, replacing its original electron storage ring with a new multi-band achromat, latest to provide extremely enhanced coherent flux and increase hard X-ray brightness by 100 times, basically replacing electron beam profile elongated horizontally to the confined spot that will us to focus beam at the end station to very tiny spot. The dark time of APS for the upgrade started in April 2023, but a year later we already get the beam back, and first light at Bandit Magnet in July 2024, and a few days later we see the first light at an undulator station, and here is a GSECARS Beamline staff celebrating this event after hard working entire year to moving all the Beamline components and replacing uh, most of them. And of course, we are celebrating with a sparkling wine, not alcoholic. Here you can see a schematic illustration of our beamline station. We have two independent undulator, counted undulator that provide two X-ray beam forwarded to IDE station for the microprobe and exhaust experiment. And at the same time, we can run either IDD or IDC station that share beam time between three different programs: Diamond Anvil Cell, Large Volume Press, and Surface Scattering. As you can see there, our brightness increased significantly, more than 100 times. And I would like to note that GSECARS, we have a unique station where we can have multiple technique available at the one sector, that is X-ray diffraction, surface interface, microprobe exhaust, tomography, large volume press, and diamond tunnel cell, basically covering studies for the entire Earth from the inner core to the surface. The diamond anvil cell technique requires dedicated station, beamline station, and the main reason for that is we have to focus X-ray on the sample inside the diamond anvil cell. But due to high refraction index of the diamond, visual and the real position of the sample is different, and it's very important when we want to combine multiple optical axes like X-ray, laser spectroscopy, and imaging with a submicron precision that require dedicated tools developed at the beamline. At GSECARS, we have a 3 beamline station where we are running a diamond tunnel cell program. Main of them is a 13 IDD, where is a high energy X-ray focused down to less than 2 micron. And mostly we are running X-ray diffraction and X-ray emission spectroscopy technique combined with online laser heating, Raman, and visual infrared spectroscopy. And we can run samples in the entire range of crystallinity from amorphous to nano to polycrystalline and single crystal. And Stella Harrington is the main person to contact to run experiment at IDD station. At 13 BMD station, we have X-ray combined with a Brion spectroscopy to study elastic property of the materials. At the same time, we can get the density and the phase recognition from the X-ray diffraction technique. Yang J is a main person responsible for this station. At 13 BMC station, we have fixed energy at 29 kV and beam size around 10 micron. And most important that we are using 6-axis diffractometer that allow us to study full reciprocal space of the sample and be able to rotate sample and detect on different position. And Dongzhou Zhang is responsible for this station. And of course, if you have any questions about where to run your experiment, you contact me. As I have mentioned, a certain BMC, it's dedicated for the high resolution crystallography using 6-circle diffractometer. Uh, the energy is at 29 kV, allow us to have high resolution diffraction with a very reasonable small beam size around 10 micron. We can use a silicon cadmium telluride detector, and we can change different environmental conditions for the sample. As you can see on this picture, we can run an external heated cell, and we have observation optical system to see the sample, as well as do simple Raman and one-side laser heating. Because we have quite a bit of space, we can run also a compact cryostat and do laser heating. And here is an example of single crystal of the materials that we are collecting at this station. And you can get more details if you look on these papers. At certain BMD station, we combine X-ray diffraction with Brilliant spectroscopy. Just quick reminder that what about the Brilliant spectroscopy? The laser light can interact with a phonon density fluctuation in the sample and scatter it with a Doppler shift frequency that in symmetric platelet geometry that's shown here. The Brilliant shift is directly proportional to the acoustic velocity. When we know the velocities, we can easily derive the bulk modulus and get full single crystal constants. But as you can see, to calculate elastic moduli, we have to have a density. That's why it's important to combine with X-ray diffraction techniques that for materials at high pressure and temperature, we can directly get the density of the materials and have a phase identification. The system is quite complex, but it's very easy to use at GSECARS. And here's an example of experimental data that we are collecting, like a single crystal from the MGO. We get orientation of the sample from X-ray diffraction and density. Here is the Brilliant spectra, and here is how sample looks like. So it should be very transparent, at least 50 micron in the size. And just after the recent upgrade, we have significantly reduce the focal spot in horizontal direction. Before it was 6 micron, now we can get 2 micron beam size, and just like yesterday we was be able to focus beam down to less than 1.5 micron. And here is an example of the data that we first was collected after a beam APS upgrade. We can see amorphization of the sample and the diffuse scattering get very well visible. Recently at certain BMD station, we have developed quite a unique combination of the tomography and single X-ray diffraction technique. As you can see here, we can do X-ray diffraction from the sample, and also we can run the tomography setup. And at BMC, we can do radial diffraction of the sample. It's important when we want to study inclusion in the material, like diamond inclusions. And when the inclusion inside the material, we a priori don't know where is the location to put on the rotation center. So running 3D tomography, we can reconstrain the entire 3D image of the sample and find the inclusion that we want, and bring it to the rotation center and get very high resolution single crystal data and identify the sample inside the diamond cell without destroying it. And that technique is available, and Stella Harrington and Mark Rivers are promoting this technique. Our main station to run diamond analysis experiment is 13 IDD, where we have very high energy X-ray and high flux beam tightly focused on the sample. As you can see here, we have very easy access to the sample position for users. X-ray coming from the right, hitting the sample, locate the diamond cell, and in the water-cooled holder, and the left side is a detector, and all the laser optics on the uh, back side. And on the back side, it's quite complex, but usually it's covered and users don't see it and operate only using very nicely developed graphical user interface, user friendly, and entire beamline could be operated using only one window. Uh, Beamline is very efficient, so we can align the sample as soon as you just bring it to Beamline and collect first data less than 5 minutes. That allow us to award only 1 to 3 shifts for the per proposal, and typically it's enough to run entire goal of the proposal, and the record, if I remember correct, was around 25 diamond cell per 24 hours. At this beamline station, we have a unique laser heating system where we are using flat top focal spot, and that allow us to collect X-ray diffraction data from the uniformly heated sample within the X-ray size beam. As you can see, X-ray inside the flat top heating spot. It means that lateral temperature distribution is a minimal. And in automatic mode, after you can press a button and it will turn on laser, collect X-ray diffraction pattern, measures the temperature, show you on the screen, and you can focus only on the scientific point of your research. Due to limited time, I will show you only one scientific example, and it's about superionic ice. Uh, that characterized quite unique state of matter. In superionic state, water molecule break apart and the oxygen ion crystallize in the lattice that is solid, but the hydrogen ion float around freely within the oxygen lattice. So it's quite interesting phase, was not easy to handle at the beamline. Even these days, upcoming very controversial result on this phase. Was be able to hit the sample at up to 150 GPa and found the phase transition. So as you can see, and you know, ICE 7 or ICE 10 at these conditions has a very simple cubic structure BCC, but when we hit it to above 3000 degree, we can see transformation to FCC phase. So it's first order phase transition, and collecting multiple data was be able to find that I7 transformed to BCC superionic ice and actually has a phase transition to FCC superionic phase, and actually it's cross Ranus and Neptune terms, and that may bring us to the conclusion that conductive nature of the superionic phase could be responsible for generation of the magnetic field of the ice giant's planet. As I have mentioned, to take full advantage of OPS upgraded beam, uh, we are upgrading our beamline station. And one of the reason, if we are doing experiment at terapascal pressure, we're using double stage anvil, like, and the sample size around 1 micron. And after laser heating, we have a multiple phases. As you can see here, it's only 50 micron. And when we zoom in, we see multiple phases. We decided to upgrade our focusing system and replacing our KB old system with a unique pre-shaped elliptical silicon double KB mirror system. And that should allow us to focus beam down to 300 nanometers. To handle such a small beam, especially when we are collecting single crystal diffraction data where we need to rotate a sample at up to 70 degree with a high precision, so the sample should stay on still rotation center with a less than sub 100 nanometers precision. We have upgraded our sample stage stack, adding Aerotech rotary area bearing stage for high accuracy continuous rotation, and also introducing slip ring, where all the wires from the top stages coming through the rotation stage without leaving any cables, so that our rotation is very high, stable, and no wobbling. To increase resolution of our X-ray imaging, we have upgraded our Pilatus X-ray detector with a new IUCr DAC cadmium telluride 9M that has a much smaller pixel size, only 75 micron, and it has that time-free readout, and you can see the clear difference between the new IUCr detector and the Pilatus detector. The first experience that we did after APS upgrade, there was easy combination of laser heating with this detector. We can immediately see the melting of the materials. And when we study the perovskite, you can clearly see the triplet splitting on the perovskite peak that comparing that was before. It is very important to know the temperature of the material during laser heating in diamond anvil cell. And usually what we can do is feed thermal radiation with a Planck distribution. Of course, if you have a very good system optical response, we can feed the gray body fitting the emissivity and the temperature and get very nice fit. But what we typically assuming that emissivity doesn't change with the wavelengths and temperature. And to avoid that, we have decided to do a new development. We may use supercontinuum laser to measure absorption and reflectivity of the samples. You can see supercontinuum laser has very nice intensity in the visible range and infrared, and if we can combine with the laser heating, we can measure absorption and reflectivity of the sample during laser heating, and applying simple consideration, if enough absorption and transmission, we can get emissivity of the sample and use it for the temperature fitting. So we are upgrading our optical system. Almost all the optics are replaced with a new one after 20 years of use. Some of them even more than 30 years old. So we have a new spectrometer. All our optics will be held using stainless steel post to increase stability, and we also will add supercontinuum laser for simultaneous measurements. Submicron beam and high stability of the optics require good support, and we have decided to replace our table with a new granite tables, and we divide it on two. One of them is called optics, and second one is holding X-ray optics KB system, sample stage, and detector. Now a few pictures. As you can see, in 2003 we have this type of setup, and in 2004 it was upgraded to the one table where the all optics is sitting in enclosure. That setup was working until 2024, and here is a last image that we took in March this year. As you can see, it's slightly updated, but it's still the same. And we start process of removing everything in April 2025, and then you can see by the end of this month it's almost empty. And here is a happy Stella to see the first time the empty station. And after cleaning it up, we get the new tables moving in. It's actually not easy to move 8,000 pounds of table to move around. And in July 2025, we already get one table. Here is a picture I took yesterday. As you can see, we already have two tables in. We start alignment of the optics and KB system and the sample stage. If you compare it to the previous one, it's quite similar, but the performance that should be much better with a new optics and a new granite table. The commissioning time with the user is scheduled for November, December this year. At the end, I would like to say that the DAC program GSECARS provides state-of-the-art experimental technique to study key geoscience topic in the entire pressure temperature range of the Earth, shallow and deep interior with comprehensive characterization of material and situ at extreme conditions. And if you have any question, I would like to use our facility, please contact me. Thank you.